Here is Yuting Wei from Stats and Data Science Department at Wharton Business School from University of Pennsylvania. Yuting is interested in high-dimensional statistics, reinforcement learning theory, and diffusion models. If you were in the tutorial week, Chapa actually mentioned quite a few works from Yuting on settling down the sample complexity for RL. And today she's going to talk about towards sample efficiency in RL, a fresh look at Q-learning. The floor is all yours.
Okay, thank you everyone for coming, and I want to first thank the organizers to put together such a wonderful workshop, and it's always super nice to be back to the beautiful University of Cambridge. So I feel lucky to speak after Xunyu and Patrick, because Xunyu has kind of set up the framework for Q-learning for me, so I don't need to motivate that much. And after Patrick's talk, I realized that I thought I was the bridge between these two. As a statistician, then I realized actually I'm invisible in the corner as a statistician. Okay, so first I want to acknowledge my wonderful collaborators. Gan Li, my former postdoc, now is a faculty member at UHK, and Changxiao Cai, who is now assistant professor at Michigan, and Yuezhe Chi, our collaborator who's at Yale Statistics, Yuxin Chen, my colleague at UPenn. Okay, so these are my collaborators of this the project that I want to talk about today. So for this audience, I don't think I need to spend a lot of efforts motivating the success of reinforcement learning nowadays, because like after AlphaGo, reinforcement learning has experienced major growth and innovation, and it has played now an important role in different application domains. Just one note, in parallel for RL to development in other areas, RL has now become integral to the rise of foundational models. RL, for example, RLHF, which is RL with human feedback, now plays a fundamental role in aligning language models to human value and communication norms. And also RL principles have now guided the models to do reasoning and optimization for long-term objectives. Okay, so although RL is without any doubt very successful, but it also faces many challenges. In this talk, I will focus my attention to one such challenge, which is the data efficiency. Okay, so in many application domains, especially the ones with human data, collecting the data samples can be expensive or time-consuming. You're dealing with human data, so it's important to think about those. And often the case because we're dealing a very large-scale problem, so the state space you use to model the problem and action space that characterize your action can be extremely large. So that's also caused some problems when we design RL algorithms. And also, in addition, I want to make the so-called data exhaustion. So the data exhaustion is the concern that people think that we're gonna run out of data, run out of high quality and human collected data when training large language models. Some researchers even predict that we're gonna run out of those high quality data in 2026. So we're gonna look out for that. So the challenge as a result is how to design sample-efficient RL algorithms. That would be the focus of today's talk. So RL is not a new topic for us because there has been a lot of landmark results even in the 70s and 80s. So, but those results mostly from stochastic control community, and those results are mainly asymptotic in nature, in the sense that it characterizes the performances of many algorithms when you have infinite amount of data and the algorithm runs at an infinite number of iterations. Okay, so that provides us with some kind of comfort and assurance that at the end of the day, your algorithms will eventually converge. However, in modern AI era, the paradigm has kind of shifted from the symptotic to non-symptotic nature, in the sense that if you don't have infinite amount of data because you are looking at very high scale problems, and you don't have that many resources to run them forever, and how do you know their performances? Okay, and also, in other words, if you have two RL algorithms, you know that at the end of the day they will converge. How do you compare them if you only have finite time and finite samples? Okay, so that motivates us to develop finite time and finite sample analysis, leveraging the tools from high-dimensional statistics and high-dimensional probability. So in this talk, I will focus on the sample complexity issue through the lens of a classical Q-learning algorithm and its variants. So as I mentioned, it's very nice to speak after Xunyu so that I don't need to spend too much time setting up the framework, which I usually find is the hardest in my talk. Okay, just one quick, maybe two quick slides just to make sure everybody is on the same page. Throughout this talk, I will talk about infinite horizon single agent Markov decision process, as is usually used to as a very simple simple setup to look at RL problems. Suppose you have the single agent which interacts and try to learn a policy in the changing environment, and at time t you observe the state as st, and you try to take an action according to at, according to some policy we call it pi, and then you receive an immediate reward rt at time t, and then the environment makes transition to the next state. So the transition st+1 is generated from some unknown transition kernel or transition probability matrix. Okay, so we are interested in the value function and the Q function, where the value function is defined as the expected cumulative discounted reward. Okay, so here this gamma is a factor, is a number, as a scalar between 0 and 1. It's often referred to as the discount factor, where it measures how much a dollar in the future means to you now. Okay, of course you can imagine that is you can always put this dollar if you have a $1 in the bank, and then accumulate the interest of that dollar. So $1 in the future will have less value to you now. So so you look at this expectation of gamma t times RT, condition on your S0, the initial state being some particular S. Okay, so that's the value function, and the expectation is taken with respect to the entire the random list in this Markov chain, in the sense that you have some random list in the transition between your states, and also random list in choosing your policies according to, choosing your actions according to some policies. Okay, and we call this effective horizon as 1 over 1 minus gamma. That sort of, it serves as an upper bound for your value function, because your immediate reward lies between 0 and 1. Okay, so the summation of this cumulative summation is bounded by 1 over 1 minus gamma. And that represents kind of the effective horizon compared to the infinite horizon setup. Okay, that's essentially after this many 1 over 1 minus gamma number of steps, the other values doesn't matter anymore because you have a geometric decay. All right, so that's the value function, and the Q function is very similarly defined. It's just when you condition on the first state being S and the first action being some particular action A. So the Q function is a function of S and A. All right. So our goal is to figure out an optimal policy in this changing environment, and we denote the optimal policy as pi star that maximizes the value function. And of course, pi star is a function of S. So for any starting state S, you have an optimal policy pi star S. And we denote the optimal value function and optimal Q function as V star and Q star. And the goal is to find pi star. Okay, so now the Q-learning algorithm is widely used and really classical algorithm, and it first originates to Watkins thesis, and then officially published in the paper by Watkins and Diane. So it's a really beautiful algorithm, which is an instantiation of stochastic approximation by solving the Bellman equation. I think Xunyu also mentioned that. So the Bellman equation in the discrete time is defined in this way. You have the Bellman operator T applies to the Q function Q equals to Q. Okay, and the Bellman operator T is defined as taking a one-step look at your reward. You obtain an immediate reward and plus this gamma times the reward that you're gonna get by making a good selection, by choosing the correct action for your Q function, by maximizing the Q function, in other words. So Q-learning corresponds to this form. It's an iterative algorithm. So if you're given a transition as A to S prime, and then you update the Q function at SA by this step, and our T of T is an estimate. Remember, our Bellman operator is an operator that depends on your transition kernel P, which you don't have access to. So you use your samples to estimate your transition kernel, and to approximate the Bellman operator, you end up with this iterative procedure. Okay? So this is our Q-learning algorithm. And this talk, I will touch upon two parts about Q-learning on different settings, although they are still very stylized. The first setting I want to look at is Q-learning with a generative model or simulator. That's the easiest and the most stylized setting that you can think about. What do I mean by a generative model or simulator? So this is first proposed by Kearns and Singh in the 90s. It now becomes a very it's the most easiest the easiest model that you can think about. Suppose that for every S and A pair, you have this simulator or generator, and it will generate the transition for you, the S prime, according to some unknown transition kernel P. Okay, so you feed in S and A, it generates S prime. Okay, so you might think that, okay, what's the point in studying such a simple case, such a simple model? Well, so it turns out that recent years there are still many works, many papers devoted to the study of this simple case, and which uncover some interesting phenomenon that we don't know before. So basically, although this is a very unambitious model to study, it gives us a nice abstraction that helps us focus on the exploitation part instead of exploration. And in many real case, for example, in autonomous driving and in game playing, you can actually have that simulator to generate this transition for you.
So this generative model is like a black box?
Because
you don't know this.
You don't know. Yes, that's like a black box. That's a black box that just output this transition for you.
But in a real application, for example, how do you design such a?
Oh, you just, for example, okay. So for example, you in the autonomous driving case, you just put the car in the real situation, and the S and A are the configuration of the real environment, and A is the action you take. You just observe if you move, for example, forward, what the environment will be. So that will be as prime.
You need to design that simulate, right? You means the driver or the whatever the agent need to design that, right?
It's not necessary that, for example, okay, so in the game playing, for example, you have this goal, and you have the board configuration, and you figure out, okay, what if I put a stone here, and then what's the configuration of the board will be, and you can actually observe that. Or in the robotic setting, if you move your robot towards the end of the classroom and you want to know that what's the configuration of the environment. It's still a very, very simple.
I see. So let's say in the setting of investment, then that will be just the market.
Yes. Yes.
Just the,
you just observe the market. Okay. And then in this scenario, we can simplify our Q learning, and where our Q learning will be this Q function, which is in the tabular case, you have this S by A matrix, right? And basically, this is saying that you can, for each entry of your SA, you can observe a transition to S prime and take the run your favorite Q learning on that point and update each entries simultaneously. So that is called a synchronous Q learning. So in total, the number of sample size we have will be T times S times A. Okay, so this is a tabular case so that you have finite cardinality of this of your set S and A. Okay, most simple example in practice, what you do, you should do, for example, function approximation and discretization if you have a continuous space. All right. So in this case, we are able to show that if you run the synchronous Q learning algorithm and you want to find epsilon accurate estimator of your Q star, your target, then the number of samples, remember that T, it requires is of order SA times, divided by 1 minus gamma to the 4th power times epsilon squared. Okay, so this 1 over 1 minus gamma is the effective horizon, which we assume is super large because gamma is taken to be very close to 1. All right, so this result is established both for constant and rescaled linear learning rates. I will not go into details, but these are the learning rates that we can establish this result for. Okay, so compared to prior papers on this subject, you can see that, okay, maybe I don't know, the front is probably a little slightly smaller than you can see, but if I draw them on this plot, I plot the sample complexity versus 1 over 1 minus gamma, that's the effective horizon, and you can see the prior upper bound, the best upper bound you get is of order effective horizon to the power of 5th. And we are able to show this to the power of 4th. Okay, and the minimax lower bound actually was prior established as the cube, 1 minus gamma to the 3rd power. Okay, so it's natural to ask why the Q learning seems to have a suboptimal dependence on the effective horizon. Is that an artifact, or is that an analysis artifact, or is that something like critical associated with the design of Q learning? Is the question clear? Yes? Okay. So it turns out that in the paper by Martin Wainwright in 2019, where he showed a toy example where he constructed a very, very simple two-state Markov decision process where you can see the transitions are drawn on the left plot, and where he plots the sample size versus the sample size needed to get an epsilon accuracy versus the effective horizon, where he calls this discount complexity the same 1 over 1 minus gamma factor, and he plots that this sample size should scale with 1 over 1 minus gamma to the 4th power. Okay, and in this paper, he posed kind of an open question and asking whether n should scale with the number of the sample complexity for Q-learning should scale with the 4th power of the effective horizon. All right, so in fact, we are able to answer this question by construct an MDP, and I will show you this MDP is similar to what Martin has drawn in his paper, but you have some extra states and extra actions. And for this MDP, we're able to show algorithmic dependence lower bound, in the sense that we construct this MDP and show that if your number of samples is below this level, this 4th power, and then your synchronous Q-learning cannot find the epsilon accurate estimator. Does that make sense? Yes, question?
I'm just curious if I understand the diagram. There is sort of this state 3 where you just stay in state 3 all the time. Is that right?
That's right. Yes, yes, yeah. This
like
is,
it shouldn't matter.
yeah, this is constructed only for to deal with a corner case for some particular choice of step size. Yes, but in practice it doesn't matter. Yeah, this is our analysis. Yeah, other question? Okay, so which means that this is an algorithmic lower bound for your Q-learning algorithm. So our analysis for the upper bound is not loose in the sense that it has to be this 4th power dependence for Q-learning. So to put everything together, we established this matching lower bound and upper bound in a very stylized setting for the synchronous Q-learning with a generative model. Question, yes?
So is there an intuition where this extra factor of 1 over minus gamma comes from?
Yeah, that's a very great point, which I will talk about in a minute, where we didn't coordinate. Okay. Okay. So why Q-learning is suboptimal? Well, so this sort of related to a previous paper, very nice, two nice works, where they empirically find that Q-learning seem to overestimate your the true Q function, where the reason is because in the Q-learning, you are targeted at the maximum of expectation of your random variable. However, okay, so that's the Bellman, sorry, not the Q-learning, the Bellman operator, you have the maximum of expectation. However, the expectation is replaced by the empirical estimate. And you're taking maximum of bunch of empirical estimate. So that overestimate your Q function. So that you sort of need to use more samples to correct that. Okay, in this plot, you can see that if your Q, you're choosing the argmax of Q, this is the correct arrow bar. But if you use the maximum of Q function, you have a much overestimated value for that. I can talk about this in more details if we have time. Okay, so if you want to get a tighter dependence for Q, then you need to incorporate the so-called variance reduction for your Q-learning to get a sharper dependence on the effective horizon. Okay, so I will mention that later. Okay. Any question before I move on to the second part? Okay, if there's no question, let's switch gears and talk about Q-learning with Markovian samples. That's a more realistic setting. So remember that previously the Q-learn, we should deal with Markovian sample because effectively this is a Markov chain. You shouldn't assume that you can find a generator to output as the transition for you at each SA. In fact, what you are given should be this Markov chain where you just interact with the environment and try to make decision. Okay, suppose that my state, action, and reward are induced by this Markov chain and induced by some behavior policy pi b. Okay, now my goal is to find the optimal policy pi star. Of course, pi star can be very different from your behavior policy pi b. And we want to learn the optimal value function and Q function. Okay, so because we are dealing with this Markov chain, there are several key quantities of the sample trajectory that our theory will depend upon. The first one will be the minimal state action occupancy probability, which corresponds to the stationary distribution of your S and A pair. So you just look at your observation, this Markov chain for observed data, and at some point will stabilize, and this will stabilize to some stationary distribution, and you look at the minimum value for that, minimal entry for that stationary distribution. And the other key quantity will be the mixing time. We call it T-mix. Okay, so again, this is our Q-learning, and this Q-learning is now asynchronous in the sense that if you have this matrix S by A matrix, depending on the trajectory, you update this different entries of your Q function following the trajectory. First, you update S0, A0, the corresponding entry, and then S1, A1, and then you jump according to that Markov chain. Okay, so okay, this is off policy in nature because your target policy is different from your behavior policy. So now the question is, what's the sample complexity of this more realistic Q-learning, where there's a highly incomplete list of prior arts. Many people have looked at this problem, and including some of the participants in this workshop. And so to summarize those results, I put them in this table in terms of sample complexity. You can see maybe on the front is okay for the people in the back. So if we set the cover time, so some results are developed in terms of the cover time, not the mixing time. And the relation between these two will be, roughly speaking, your cover time. That's the time it takes to cover each state and action pair. So would be roughly T mix over mu mean. If you use that and compare the prior results, you can see that I draw one line that is linear in terms of the cardinality of S and times cardinality of A, and the best result that you have is by this Chu and the Wellman paper, 2020. They have like a quadratic dependence on S times A. And so the all prior result has at least the T mix times S squared A squared, and in this work we try to establish a linear dependence of S and A. Okay, so in particular, this is our result. So we are able to show that to find an accurate estimate for your Q star, the Q learning takes this many samples. So it's additive, it's the summation of these two terms, and one term that depends on mu, okay, so one term that only depends on mu mean, that's the minimal entry for your stationary distribution, and the other entry depends on T mix, but does not depend on epsilon. Okay, you sort of decouple the T mix with the mu mean. Okay, so now if you take mu mean to be 1 over S times A. Okay, because that's you have a stationary distribution supported on S times A many entries, and the mu mean should be at least of order 1 over S times A, and plug that in, you get a SA. The first term will scale linearly in terms of S times A. Okay. Okay, you can see that compared to the prior art, you get a sharper dependence on T mix and mu mean by separate them out into two terms and having one term that only depends on mu mean. Okay, let me sort of quickly unpack the second term. This T mix divided by mu mean times 1 minus epsilon, 1 minus gamma, that does not depend on your accuracy level epsilon. And that reflects the cost it takes to reach a steady state. And once you reach a steady state, this the second term sort of vanishes, and it becomes amortized as the algorithm runs. And the first term will be the dominant term. And this dominant term, as I mentioned before, scales linearly in terms of 1 over mu mean. And if you wish, you can plug mu mean as 1 over S times A. So you have a bond where the sample complexity scales with SA divided by the effective horizon to the 5th power times epsilon squared. Okay, and now if you compare to the minimax lower bound, actually if you work a little bit harder, you can tie this 5th dependence to the 4th dependence, as in the synchronous Q-learning case. So you can work a little bit harder to get a 4th dependence for the asynchronous Q-learning as well, but still, if you have compared to the minimax lower bound, you still have a gap. So to tighten this gap, you can use the variance reduction idea inspired by Johnson and Zhang's paper. It's a very, very impactful paper in 2013. And Martin's paper in 2019 also adopt this strategy to sort of achieve a better dependence on the effective horizon. Okay, so let me conclude. This talk, I touch upon Q-learning with 2 different settings. The first setting is the simulator setting, where this is a super stylized setting, and we are able to answer the question that Q-learning is actually not minimax optimal. It tends to overestimate your Q function. And the second setting, we provide a sharper characterization of Q-learning with Markovian samples in the sort of decouple the role between mixing time and the mu mean. And to summarize, I think understanding non-symptotic performance of RL sort of connects the stochastic optimization and high-dimensional statistic and high-dimensional optimization, which offers a nice playground for us. And thank you for your attention.
Thank you, Yuting, for the very nice talk we had.
I loved your talk. It's a really nice scholarly lecture. Just a challenge for everybody. If you replace that L-infinity norm by an L-infinity span norm, then all the 1 over 1 minus gammas go away.
Oh.
You know, and so it's just like we haven't reached success when we get 1 over 1 minus gammas for Q. It's because of the fact that it's just one constant. It's the average cost of 1 minus gamma that blows up when gamma goes to 1. And so all of that complexity is just an estimated constant. And so, and we don't care if the span norm is enough, because if we get Q plus a constant, we get the upland policy. So we don't care about constants.
I see.
So it's just like I've been trying to push that to everybody.
Yeah, great point. Yeah, that's a great point.
And I know that the proof would just go through. We just go through and ignore constants. It's the same.
Very nice. Good point.
So when you have like very good cover time, like arbitrary values, that like they prefer like I have like very periodic chain, and the mixing time is arbitrary, but you said
actually in our paper we have a result that writes the sample complexity in terms of the covering time as well. Yeah. Good point.
I have a quick question. So for this last part, when you improve the results from Chu and Weirman, the algorithm exactly the same. It's just proof technique is different.
Yes, exactly.
If no further questions, let's thank Yuting again for the wonderful talk, and then we can continue the discussions during the lunch break.